Welcome to a deep dive into Project Nemesis Vector, a speculative yet visionary aerospace engineering concept. Inspired by declassified UAP records and decades of propulsion research, this project imagines a future where flight is no longer bound by conventional thrust. Instead, it explores the possibility of manipulating inertia and electromagnetic fields to achieve silent, agile, and trans-medium flight. While the technology remains theoretical, the ideas presented here offer a glimpse into what the next generation of aerospace vehicles could look like if breakthroughs in quantum vacuum engineering and advanced materials become reality. Let's embark on this journey through the architecture and science behind the NVX-12 Astraeus. Throughout the 20th and early 21st centuries, aerospace researchers and military analysts have studied countless reports of unidentified aerial phenomena. These craft often displayed flight characteristics that defied conventional physics: abrupt acceleration, silent hovering, and seamless transitions between air and water. Programs like Project Blue Book and AATIP fueled speculation about new propulsion methods. Project Nemesis Vector builds on the hypothesis that future breakthroughs may involve direct manipulation of spacetime, plasma fields, and inertial frames. Rather than a traditional aircraft, Astraeus is envisioned as a field-dominant platform, setting the stage for a radical shift in aerospace design. Astraeus's quantum flux core is a speculative system designed to interact with zero-point vacuum fluctuations. The idea is that under extreme electromagnetic resonance, vacuum energy density fluctuations could become accessible for energy transfer. The core includes Casimir resonance chambers, quantum lattice resonators, and superconductive flux loops. Harmonic synchronization between these components and the plasma toroids is managed by AI, aiming for stability and potential spacetime gradient manipulation. While entirely theoretical, this approach hints at future energy architectures beyond chemical or nuclear power. To power its advanced systems, Astraeus integrates a compact aneutronic fusion reactor, superconductive capacitor banks, and a quantum flux augmentation core. The fusion reactor operates within a magnetic confinement chamber, utilizing boron-hydrogen fusion for high energy density. Power is routed through superconductive conduits, with an AI continuously balancing plasma demands, flight stabilization, shield generation, and thermal dissipation. Redundant ultracapacitor arrays provide emergency power during field collapse or plasma instability, ensuring operational resilience. Building Astraeus would require manufacturing capabilities far beyond today's aerospace industry. Essential technologies include room temperature superconductors, high-strength metamaterials, quantum-scale fabrication, and AI-directed assembly. The craft is constructed from modular segments, central energy core, plasma toroidal assembly, whole metamaterial segments, sensor lattice systems, and AI processors, all interconnected by a superconductive neural architecture for real-time field balancing and adaptive energy routing. Despite its promise, Astraeus faces significant engineering obstacles. Plasma instability, thermal overload, electromagnetic interference, material fatigue, and quantum coherence loss are all critical challenges. Overcoming these would require breakthroughs in materials, science, energy management, and field control. The project's speculative nature highlights the gap between current capabilities and the demands of such advanced aerospace systems. If realized, the Nemesis vector architecture could revolutionize aerospace engineering. Scientific applications include deep space exploration, planetary research, and autonomous orbital construction. Civilian uses might involve high-speed global transport and disaster response. For defense, persistent surveillance, electronic warfare suppression, and rapid deployment would become possible. Future variants like the NVX-18 Leviathan and NVX-30 Hyperion expand the platform's reach into heavy lift and deep space missions. Astraeus's primary systems are designated with specialized technical labels. The drive system is the EIFD-9 Electrodynamic Inertial Field Drive. The AI system is Nemesis Q Autonomous Harmonic Intelligence. The reactor is the QFC-3 Quantum Flux Core, and the hull is the MMS-7 Metamaterial Shield Matrix. Each subsystem is engineered for integration, supporting the craft's unified field-dominant architecture. The NVX 1-2 Astraeus is theoretically capable of exceeding Mach 18 inches atmospheric flight and achieving single-stage orbital ascent. Its primary propulsion medium is electromagnetic plasma field dynamics, with an operational ceiling extending into exo-atmospheric space. The hull is made from a graphene titanium metamaterial composite, supporting both autonomous and crewed missions. These specifications underscore the ambitious scope of the project. Key flight assemblies include the TVA 11 Toroidal Vector Acceleration Ring, IFR, 2 Inertial Flux Regulator, PCE8 Plasma Compression Emitter, GSN4 Gravitic Stabilization Nodes, and QHR6 Quantum Harmonic Resonator. Each subsystem plays a critical role in plasma circulation, inertial balancing, and field synchronization, forming the backbone of Astraeus' advanced propulsion and control architecture. Astraeus' internal structure is divided into 4 main sections: the upper dome houses hyperspectral sensors and quantum LiDAR. The central command core contains AI processors and pilot interfaces. The mid-core engineering ring supports superconductive assemblies and cooling channels, and the lower vector chamber manages plasma acceleration and boundary layer stabilization. This layered approach ensures optimal system integration and crew safety. Astraeus' flight sequence begins with core initialization, activating superconductive harmonics and stabilizing temperatures. Plasma ring activation follows, generating circulation in the toroidal ring. Harmonic synchronization aligns electromagnetic frequencies, while the plasma field expands to form a boundary envelope. Inertial gradient modulation redistributes inertia, enabling vector translation. The adaptive plasma sheath minimizes turbulence during high-velocity ascent, supporting seamless atmospheric transition. Astraeus' metamaterial hull and plasma envelope are designed to disrupt radar by absorbing electromagnetic frequencies and diffusing reflected signals. The plasma-assisted thermal diffusion layers reduce infrared signatures, while field-dominant propulsion minimizes acoustic emissions. Electromagnetic harmonics can generate localized sensor interference, potentially disrupting communications, saturating sensors, and generating electronic decoys for enhanced survivability. The Nemesis Vector framework supports multiple future variants. The NVX-3 Spectre is a compact stealth reconnaissance platform, while the NVX-2-1 Atlas is a heavy-lift transorbital carrier. The NVX-50 Dominion is an experimental deep space exploration craft. Each variant is tailored for specific missions, leveraging the core field-dominant propulsion and advanced materials of the Astraeus platform. Project Nemesis Vector draws on a wide range of scientific domains: magnetohydrodynamics, electrogravitics, quantum field theory, vacuum fluctuation studies, superconductive energy systems, plasma confinement physics, advanced metamaterial engineering, and AI-directed aerospace control. These inspirations form the conceptual backbone of the project, blending established research with bold theoretical extrapolation. Astraeus' propulsion relies on nested electromagnetic compression geometries generated by counter-rotating superconductive toroidal assemblies. The resulting field effects include plasma confinement, boundary layer ionization, airflow stabilization, and dynamic charge asymmetry. The plasma envelope acts as a dynamic shell, reducing drag, radar reflectivity, and thermal buildup, while stabilizing hypersonic airflow and minimizing underwater cavitation. A speculative subsystem within Astraeus proposes that high-energy rotating electromagnetic harmonics may weakly interact with local spacetime geometry. Theoretically, this could reduce apparent inertial loading, enhance acceleration tolerance, and enable field-mediated directional translation. While these effects remain unverified, they represent the cutting edge of propulsion theory and the potential for revolutionary flight dynamics. Astraeus supports multiple flight control modes: atmospheric stabilization, silent hover, hypersonic translation, transmedium penetration, orbital ascent, autonomous reconnaissance drift, and harmonic jump translation. Each mode leverages different configurations of plasma vector emitters, magnetic balancing, and field harmonics to optimize performance for specific environments and mission profiles. The theoretical framework of Astraeus is grounded in advanced mathematical relationships. These include the Lorentz force, electromagnetic energy density, Casimir interaction, relativistic energy, and oscillating harmonic wave functions. These equations underpin the craft's plasma confinement, electromagnetic acceleration, vacuum fluctuation theory, and harmonic field synchronization, providing a scientific basis for the speculative propulsion concepts. Astraeus's energy systems include compact aneutronic fusion, superconductive energy storage, magnetoplasma dynamic recapture, thermal gradient harvesting, and ambient electromagnetic harvesting. While quantum vacuum energy extraction remains hypothetical, these systems collectively aim to maximize efficiency and resilience, supporting the craft's demanding operational profile. The structural materials of Astraeus are at the forefront of material science. The graphene titanium lattice provides strength and low mass, while boron nitride nanotubes offer thermal resilience. Metallic glass alloys and aerographene foam structures enhance elasticity and conductivity. High-entropy alloys and metaceramic thermal layers withstand extreme environments, and programmable smart materials enable adaptive hull properties. Astraeus's steering relies on differential plasma vector steering, magnetic pulse steering, dynamic center of field translation, rotational harmonic steering, and multi-axis field pivoting. These systems allow for simultaneous vertical lift, lateral translation, rotation, and hover stabilization without conventional aerodynamic surfaces. Plasma weight compression and inertial dampening further enhance maneuverability and crew safety. Astraeus incorporates quantum-assisted navigation, distributed sensor skin, adaptive optical camouflage, directed energy concepts, resonant structural stabilization, cryogenic superconductive infrastructure, autonomous repair nanostructures, and electromagnetic environmental shielding. These emerging technologies collectively support the craft's advanced operational capabilities, resilience, and stealth. Let's visualize the Astraeus craft with a detailed technical cutaway. This cinematic rendering reveals the internal arrangement of superconductive rings, plasma chambers, AI processors, and sensor arrays. The glass-like imagery highlights the integration of advanced materials and field systems, offering a glimpse into the next generation of aerospace engineering. This next-generation blow-up image provides a labeled, realistic view of the Astraeus's internal systems. From the toroidal vector acceleration ring to the quantum flux core and metamaterial hull, every subsystem is meticulously arranged for maximum efficiency and integration. Such visualizations help bridge the gap between speculative theory and tangible engineering possibilities.